Okay, right now it is March 15th, and I'm going to do another rap video. Here's my plan. I'm going to do a bunch of rap videos on physics, chemistry, and biology. Each subject 3 videos, 1 elective and 2 cores. I'm going to talk about the core parts really fast, so 9 rap videos, and then I'm going to do past papers. I'm going to do an English paper on video, math paper 2. I am going to be doing physics, biology, or chemistry. Yeah, and an LS potentially. So, anyways, today I'm going to do the physics electives wrap, where I sort of thicken my own knowledge for the physics electives paper. Basically, during the day of the physics exam, there are 2 papers. One is paper 1. 1A is multiple choices, 1B is the long questions, and then we have paper 2, where they give us 4 large questions, and each large question has 8 MCs and 2 large sub-questions, which has a few sub questions and sometimes sub questions, and altogether it's around 40 marks. And in those 4 big questions, we all need to choose 2 in order to fulfill the 40 mark, because each big question is 20 marks. So we chose energy and medical physics, and not shit. All right, I was fast. So yeah, energy and medical physics. Some people, so me in my class, our physics teacher, we decided to choose medical physics. Energy is really necessary because it's easy and it's basic, and the other class chose atomic physics, which I think is incredibly boring, but it apparently is easier than medical physics. But either way, let's talk about the energy first, which is E3 out of 4. We have E3. Okay, so you can see there are 4 electives. Astronomy is incredibly difficult, as interesting as it sounds. Book 2 is Atomic World. That is the other class, and all of us had to do energy, and we took medical physics as well. So energy. We also have a very shitty supplementary notes that is actually looks shitty, but it's actually very useful. But still it looks bad. So we have the book. So let's start off with also later on I'm gonna do a physics electives past paper. So let's start off with electricity at home. Kill me. So the first thing that we need to know is that there are energy consuming appliances at home. Not much. Electricity, oil, and coal products. I must yawn. I'm running out of oxygen. P times T equals to energy output / input. P being power, T being time. So power times time equals to energy, and energy divided by time is power. Cooking without fire. We have an electric hot plate. We have induction cookers. And for electric hot plates, they basically heat up a friggin' plate. And for induction cookers, we have a metallic plate, a metallic base, and there's a magnetic field produced by an AC current, and alternate current, and so a magnetic field is generated, and then an eddy current is generated in the metal base, and that eddy current just produces heat. So that is induction cooker, because it's all induced heat induced by magnetism. That is awesome. Well, microwave ovens, we got some microwaves in the microwave. Essentially, essentially a bunch of microwave comes in and like heats things up. So it's pretty easy. So electric hot plate converts electrical energy to internal energy, and then some heat's lost to the surroundings, and then we have the internal energy of the cookware, and then induction to the conduction to the food. The most efficient, though, is induction cooker. Some heat lost in the coil, energy in magnetic field, some induction, more conduction, some heat loss to surroundings. A microwave oven is the least efficient, with other electricity going to, the lamp, the turntable, the clock dial. There are some energy lost in just generating microwave, and again, he lost his surroundings. So we have a chart of that compares all of these three types of cookers. I'm already 7 minutes in. I haven't even finished chapter 1. God dang it. Air conditioning. Oh yeah, this is important. So heat travels from a hot body to a cold body, and okay, this is how an air conditioner works. But basically, the heat is removed from a hot room. Say there's a hot room, and then more heat is removed from the hot room by the cold water or refrigerant. And first of all, the refrigerant is heated up because it just absorbed a bunch of heat from the hot room. And then there's an expansion valve that expands the air to make it even hotter, so that later on when it is exposed outside, it will lose heat. And then later on, all the heat is lost and it's compressed again to become something super duper cold. And that is how an air conditioner works. Now, we got some conditions of the refrigerant at different stages. The refrigerant turns from liquid gas mixture to gas, and then become liquid again after the condensation. And the internal energy changes a lot as well. Yeah, that's all we need to know. We have the cooling capacity, which is basically a maximum amount of heat removed over time, and that's pretty much it. Okay, we got the COP, coefficient of performance, and that is cooling capacity over electrical power input. So that is energy over time over power, which is power over power, which is the reason why there's no unit, because it's power over power. But you get the idea. It's about the efficiency, the coefficient of performance. Okay, there we go. Chapter 1 finished. Chapter 2, electricity at home, part 2. Why can't it just be like one big part? Why do you have to separate it into 2 parts? I don't know. Okay, now let's talk about lights. There are different kinds of lights. Oh my goodness, I am tired. In an electron transition, an electron in an atom moves from one energy level to another. And when it moves from a higher energy level to a lower energy level, some electromagnetic waves are emitted, and those waves are light waves. Probably. Are all electromagnetic waves light waves? I would like to know that. But, light waves don't have to be, visible. That's for sure. So we have a few types of lamps. We got the fluorescent tube lamps, gas discharge lamps. The fluorescent tube lamps discharge the gas. Of course, there's the negative electrode, and there's the gas in the middle of the lamp, and the electrons sort of move from the negative electrode to the positive. And when that shit happens, some visible light just comes out, and there's that. We have compact fluorescent lamps, and we also have HID, high intensity discharge lamps. And then we have the incandescent lamp, also known as the filament lamp, where basically you heat a bit of filament like tungsten. It becomes so hot it starts to glow. That's pretty much what happens in a friggin' filament lamp. And yeah, if the filament is broken, the whole thing is burnt, and there's no point in, the lamp I have right now, it gets burnt so easily. I don't know if it's because there's no fuse, or maybe the fuse is like installed inside the light bulb, so every time it burns. But then I don't understand the reason behind, every time there's a short circuit in this apartment, this light bulb just burns out. But that's basically what's up. We also have the light emitting diodes. Hell yeah. A halogen lamp. Oh wait, halogen lamp is not a gas discharge lamp, even though it's called halogen lamp. What? Halogen lamp also has tungsten inside, though, so there's that. Anyways, LED, light emitting diodes. We have the P type and the N type. Basically, two layers of materials. One layer is being full of protons, and one layer is being full of neutrons. And when applied with the battery, the protons and the neutrons are just colliding with one another between the junctions. So EM waves, aka electromagnetic waves, sort of come out. So how do you measure brightness? First of all, we have the luminous flux in the unit of lumen. And then we have the illuminance in the unit of lux. Yes. And the illuminance, aka lux, is basically flux over surface area, which is 4 pi r cube, because we're in the 3D world right now. And so flux is how bright an object is, and lux is how much you receive it. But that is an ideal lux. And then we have the lux that is the actual lux, because I can look at the lamp right now, but what if I move my face towards this direction? The lamp is up there, but my face is looking at here, so there should be the lux that I perceive should be this cosine this angle. Get it? All right. There we go. Oh, 4 pi r cube. Shit. I messed up the sphere surface area equation. But yeah, basically there's that. Ooh, what the fuck? Alright, here is a gigantic table comparing all of the types of lamps. Also efficacy, basically luminous flux over power. Alright, we're not even in the friggin' annoying stuff in this chapter. Okay, we got a bunch of energy saving devices. Oh my goodness. Energy efficiency in building and transportation. You know what? I'm just gonna fly over this because I realize that I'm really running out of time. But basically, first of all, we get the rate of conduction because there's this unit called the OTTP. And if the OTTP value of a house is too large, then your house gets heated up really easily. So you try to keep that value as low as possible. This is a little confusing. I'm gonna use the notes. This is just as confusing, to be honest. But I don't know. This is more simplistic, I guess. Shit. There's a thing called solar constant. Where is it? Okay, here it is. You know, this is just as confusing. I'm gonna use my notebook. Alright. Oh my goodness. Alright, so we have, my notebook is just as confusing, but you know, this, at least you know what the hell's going on. Alright, so, rate of heat transfer equals to U times A times T, and that rate is also called a U value, and it is in the unit of not OTTP, OTTV. The rate of heat transfer is in the unit of watt per meter square. Is that right? Is that right? Thermal conductivity is watt per meter per Kelvin or Celsius. I'm getting confused here. But anyways, U times A times T is basically rate of heat transfer is power, because heat is energy, so the rate of heat, you know, rate of energy, hey, power, so it's in watt. But here's the catch. The OTTV unit is watt per meter square, because you basically get the rate of heat transfer and then divide the whole thing, all of the materials in the building, all of the rate of heat transfer of all the materials of the building, and you know, in the proportion of the surface area over the entire thing surface area minus the floor, unless the building is midair, then in that case the total OTTV is not in watt, but it is in watt per meter square. But how do you find the rate of heat transfer? U times A times T, U being the U value, and U value being, what the fuck is a U value? Thermal transmittance, and the unit is joule per degrees per second per meter square. And we also have the thermal transmittance is conductivity over thickness, and thickness in meter. Always keep that in mind. And conductivity is basically joule per degrees Celsius or Kelvin per second. So watt. So you can just summarize it and make it a watt per degrees Celsius per meters. And then we got the thickness. And then the U value times the temperature difference between the outside and the inside, and then times surface area, and then the whole thing over the total surface area OTTV value in the unit of watt per meter square. Hell yeah. All right. Now, what else do we have? Solar power. The thing with solar powers is that we got the N-type. Again, we got the N-type and the P-type. And the current goes from the P-type to the N-type. P being proton, N being neutron, and there's the P-N junction. And there are a bunch of holes. The N, they sort of go to P. And the reason why the N goes to the P is because of sunlight. Sunlight provides energy. The neutrons, they get excited. They try to go to the P, and when they go to the P, they generate the current, so electricity happens. We got the I don't even know how to calculate solar power, so I guess I need to look at that. We also got all sorts of transportation. So before we look at power generators, we could actually look at some transportations. So I mentioned solar constant. Basically, it's also watt per meter square, but the entire sun towards the entire 2D surface area, well, cross-section area of Earth. These are all types of not really all types, but we got a few types of transportation. Motor vehicle, electric vehicle, shout out to Elon Musk, and hybrid, basically both. And here are the pros and cons of both vehicles. You can check that out. And okay, there we go. Solar energy. Regenerative braking, right? This is a huge concept. Regenerative braking, basically, every time you hit the brakes, every time you drive, some kinetic energy is gained, and then every time you hit the brakes, the kinetic energy resisting the brakes will be stored as chemical energy in the batteries. I guess that's what it means. I don't know. Is there really no way to calculate solar power? There's a solar constant, 1366. But there's we don't. Oh shit, we do. Oh shit. Oh my gosh. Watt per meter square. Solar panel surface area, meter square. Cosine the degree against the tangent of that position times the efficiency, always, and times the total power received, which in this case should be 1366. Or solar radiation in that area in general, Okay, damn. So we got that out of the way. We also have some more renewable stuff like hydroelectric power. And the power is basically mgh over time. And the unit of watt, mgh, is potential energy loss in gravitational PE of water, m being the mass of water, g being 9.81, and h being the height. And we also have the wind power, which has the equation of 1 over 2 PAV cube. P being density, A being the surface area of the bunch of air, and V being the speed, the velocity of the air. Never mix it up with volume. Last time I mixed it up with volume, I died. And that is a wind power. That is not... Is that power or is that just energy? I think that's power, right? Well, let's find out. Oh, and times efficiency, of course. Yes, that is power. Now, the last thing on this entire book is the nuclear energy. There are different types of nuclear power plants. We have the fission, nuclear fission, and nuclear fusion. Fusion is better than fission because the binding energy is larger. More energy required to fuse them than to break them. I don't know why. E equals to mc squared. Basically, this is how a reactor should look like, and there are two circulatory systems. So we got the primary circuit. We got the control rods, the moderators, the control rods to absorb neutrons, and the moderators to slow down the fast-moving neutrons. And we also got the concrete thing, and then the whole thing steam generated goes to the turbines, and then they create they generate electricity. So there's that. That's it for the whole book and my life. Right now, let's move over to E4, medical physics. Medical physics is like a combination of physics and biology. More emphasis on the physics though. So yeah, let's go. This one is definitely more interesting than atomic physics, but it's also slightly harder. So I gotta revise the hell out of this. So we got 3 chapters, and oh boy. I have yawn problems. Chapter 1, human vision. So this is the human eye. If you've studied biology, this is basic. Alright. Okay, here we go. That's the good stuff. That's the good stuff. Lens formula. So this is the eye, and this is the object. And between the lens and the object is U, which is basically the object distance, and we got the V, which means virtual, and it's the image distance. And the image should be formed right here at the yellow spot. More like it should be focused in the yellow spot, but there are, you can also see that, image like I can right now in other spots of the eye, but like most importantly the yellow spot, the most focused. And then yeah, this is the image distance, and then 1 over U plus 1 over V equals to 1 over F, F being the focal length. And lens are convex, not concave. So, in case you're dumb and you think that lens, like our human eyes, lens are concave. Focusing on a near object, our lens becomes more concave, so lights diverge even more. And then focusing on something far away, our lens become less concave. So the light rays are almost parallel. Almost. If it's parallel, we can't see anything. Yeah. Duh. Alright, we got rod cells and cone cells. We know all that shit. All the easy shit. Rod cells works in dim lights, black and white. Cone cells sees colors, works in bright conditions. Next, the power of the eye, diopter. 1 over focal length is diopter. There's also an effect of diffraction. Okay, so S equals to R theta, which is like the thing, radiant formula or some shit. We got the Rayleigh criterion. Oh yeah, it's related to radians, which I'm not familiar with because I didn't take calculus because I'm stupid. But basically 2 points, because when we see things, diffraction occurs. But the reason why we don't see everything just chopped up in fringes right now is because our eyes are actually powerful, and S equals to R theta, and S being the distance between 2 points, R being the distance between the horizontal distance between my eyes and that object. And we can find theta, and then we can also find the theta by doing 1.22 lambda wavelength of that thing, that light, but depends on the color, of course, over D, which is the distance between your eyes. I hope they don't, ask a question related to this one, because I don't fucking know anything. Again, diopters. I mentioned that already. Alright. Optic fibers. God damn. Fiber. Oh, is this. It's. Okay. YouTube hates this. I get it. We got optical fibers. Basically, this thin tube, and then light sort of goes in and just reflects around it. We got endoscope. Basically, like this. Looks like a seahorse. I never, ever want an endoscope inside. This sounds wrong. But endoscopes are disgusting. That's what's up. Coherent bundles. If it's incoherent, you can't see jack shit. That's it, chapter 1. Alright, chapter 2. Human hearing. So just the ears, and if you study biology, you know how ears work. Mechanical waves in the middle ear with the ear bones, vibrations, and the cochlea turns the vibrations into nervous impulses. We got the exolymph and the endolymph. The endolymph sort of makes the little cilia move, and these things sort of creates the nervous impulses going to our hearing center and associative center, and now we're in biology territory. But basically there's that. We got the sound intensity level, the very iconic sound intensity level formula that I always forget. L equals to 10 log I over I naught. I naught has a value. It's a constant. And that is 10 to the power of negative 12. Watt per meter square, by the way. But I is not a constant. L is I is the intensity of the sound being emitted, and L is the sound that we perceive in decibels, because the only way to I guess make something twice as loud is to turn that something and copy it 9 times more, so that it's 10 times the thing and it's only twice as loud, because our ears are logarithmic or something. Oh my gosh. Okay, now this is annoying. Basically, what you want to do is that at exactly 1000 hertz, 1000 hertz, because different people has different curves of equal loudness, different people have different hearing abilities, but basically say you listen to a specific sound in this hertz and that hertz, which different frequency produces different pitches, and then you sort of go up and see at which. I'm already confused. Oops. Okay, I gotta look at my notes. One sec. My very organized notes says that the first thing you do is that at a specific hertz, you go up. No, at a specific hertz and at a specific intensity level. So we got the loudness and the pitch. You move that point along the curve until you hit 1000 hertz. And then you check the number of fons, which is the decibels, the corresponding decibels, which see, that is a heck of a loud motorcycle. And the reason why I'm hearing it right now is that the sound waves sort of go through the windows and the concrete of this building, which is really impressive in my life. All right, whatever. It's whatever. Oh, I did the thing. Exactly 1000 hertz. Weird. Why does it have to be 1000? Why can't it be like, I don't know, 1100? Why? I don't know. We're not even at the confusing stuff yet. Oh, now we're at the confusing stuff. Ultrasound. So ultrasound is basically louder than the audible frequency range, louder than 20,000 hertz. Actually loud. Right now, I can't listen to anything above 17,000 hertz. So, my ears be deteriorating and shit. But basically, what's up with ultrasound is that there's an attenuation. And to calculate the attenuation is Z equals to PC. Z being the acoustic impedance, and P being density, of course, as always, in the unit of kilogram per meter cube, not gram. We're not studying chemistry here. Things are in kilogram now. All of a sudden, like what the C in meter per second. Not light speed, but you get the idea. It's not necessarily velocity, so it's not V. But basically, here's what's up. Got the ultrasound. It hits something. It keeps going, but it's a little smaller. The sound is smaller, and there's that. The unit of Z is in kg per meter square per second. So there's that, and the intensity reflection coefficient, because some sounds get reflected. Intensity of the reflected pulse over incident. Reflected over incident. R over I. Always R over I. And then you can also find that by doing Z2 minus Z1 bracket square, the whole thing over Z2 plus Z1, the whole thing square. Z2 being the second medium. See, now it's confusing. We got the coupling gel. Now, what does the coupling gel do? Is that it eliminates any air between it and the transducer, because if there is air, then there's going to be a lot of feedback, because it just bounces right off the skin and then goes back up, and it's just fucking stupid. We got some piezoelectric effect going on right now, though. Quartz is piezoelectric, I don't know, because it triggers mechanical vibrations and produce ultrasound. But in order to trigger that, you gotta apply some force. stretch it, compress it, and then some charges will happen and stuff will happen basically. Now we also got some ultrasound scans, but I don't have time for that. You know what? I have time for that. This is an A scan where you can't see anything but like little impulses. And then there's the B scan where you can actually see something. And yeah, there's a table showing the pros and cons of A scan and B scan. B scan is more expensive. You can't see a baby with A scan. Spatial resolution, because you know, yeah, spatial resolution. The higher the frequency, the higher the resolution. That makes a lot of sense, right? All right, so high spatial resolution, neck, breast, thyroid, testicles. Lower when you're talking about liver and kidneys. Super low in bones and stuff, I guess. I'm really tired right now. Leave me alone. Medical imaging and using ionizing radiation. Now it's only going to get even more confusing from here. First of all, we got X-ray imaging, and there's a way to create some X-waves, and that is by emitting some fast-moving electrons from the cathode, aka the negative electrode, because this is electrolytic, and then firing them at a heavy metal target to produce some X-rays. We got an attenuation, I equals to I naught E to the power of negative mu x. Mu being some sort of constant linear attenuation coefficient, and x being the length, of course, the distance in centimeters, and I naught being the initial intensity, of course. The denser the material, the higher the attenuation coefficient, and yeah, stuff like that, you know. So of course, when you're gonna do an X-ray scan, you detect it at the back, kinda. And so if there are a bunch of bones here, it's gonna be white. If there aren't, then it's gonna be black. Half values, that stuff exists. All right. Don't take too many X-rays, it kills. We got the CT scanner as well, which, I mean, this is how you scan CT. And then we got the gamma ray scanning. Yes, that is actually possible. You basically eat some tracers, like iodine pills, and it absorbs the gamma ray and then emits it back. Where the hell is my notebook? Here's the thing with gamma radiation is that no attenuation occurs, because gamma ray attenuation, are you fucking kidding me? It penetrates anything. The good thing about gamma ray is that it is non-ionized, well, weak ionizing power, but alpha radiation scans, it's going to actually kill you. Alpha radiation scans, right, you can add some artificial contrast medium when you're talking about X-rays to highlight some organs. And then other than that, I think that's it for physics electives. So yeah, thanks for watching. I'll talk about biology electives tomorrow or something. I don't know. I don't fucking know. Leave me alone.